ว่าเมื่อกี้ผมมาโซเขาบอกว่าเดี๋ยวให้เปิดของเขาขึ้นรอได้เลยก็เลย
complicated just the underground guy.
Yeah, no, this 7,000 series is not possible to
Are you okay?
7,000 series. So this, anything is to make bigger and bigger.
Relax. Have a
เปิดบรรยากาศงานกับคืนอีกทีได้ไหมการงานวิดีโอไหนอันนี้เป็นของ2023 ครับเขาลงในแฟนไดไว้ให้เปิดย้อนไปแบบคนเยอะๆเป็นบรรยากาศงานเป็นคลิปบนนะครับแล้วก็เปิดมาเริ่มใหม่ดีกว่าโอเคยังไม่เห็น Yeah.
You're next.
Oh, right. Muscle first, right? Yeah, only two before lunch. Muscle and fries.
posted that there are more than 80 patented technology for slurry or for semi-solid or for reo-casting into the market. But if we look to the production in terms of volumes, in terms of tons produced with this technology, all those technologies are probably less than 1%. So what's the reason that in such a long time all those technologies have been not successful? Because if we look to the documentation, if we look to the experience gained in the R&D center, everybody knows that there are many benefits achievable through the reo-casting. Benefits related to the quality, first of all. So quality in terms of scrap rate reduction. Quality is related to mechanical properties. So the reduce the effect because, of course, from the filling side, you know, you have a filling less turbulent and more laminar. From the shrinkage point of view, we have a less solidification. The solidification range is smaller, so less shrinkage porosity and greater cost efficiencies. Mark mentioned that we can double or more the die life. We can reduce the cycle time. So there are theoretically a lot of achievable benefits. So what's the reason that those benefits didn't become a reality in the real production until now? So when my children don't know how to make an homework, they ask to AI, to, of course, you can ask to Gemini or to Copilot or to any other. So I did it the same. So I type a very simple question: why reo-casting is not successful? And so those are the answers from the intelligence, artificial intelligence. The first answer from the artificial intelligence is the complexity. Many of the technology on the market are very complex, very, very complex, and very difficult to apply. Why of this? Because all those technology are temperature control technologies. So it's very difficult to control the different temperature into the liquidus and the different temperature between the different solid fractions. So very complex and very tricky to apply it. Second is the request for tool change. The majority of the technology requires a different tool with thicker gates, different risers, different flow length. So you need a different die for reo-casting in comparison with the liquid die casting. Third point, a limited alloy, kind of alloys. You know that commonly we say that for reo-casting or for semi-solid is required a less silicon content. So when you use a standard alloys that you have 9, 10, 11% of silicon in your alloy, of course you have a better castability, but it's worse from the side of the reo-casting. So other points suggested. Expertise is needed, so it's not easy to implement because it's not a magic tool to apply, but a solid expertise is requested. And also, very often, it happened in the past that in laboratories, in the R&D department, everything worked well, and when they went to the productions, only very limited series have been successfully produced. in a foundry. And at the end, it means that reo-casting has been used up to now only for very, very tricky and difficult parts. Only when the liquid standard high pressure die casting was not possible to apply, or you have a so big scrap rate, or so many problems. Okay, only in that cases, foundries have tried to explore new opportunities, and among those opportunities, reo-casting is one of them. At the end, probably this is the most important point. Underappreciated advantages. When I travel around the foundries in Europe, I realized that there are still a lot of confusion. A lot of confusion among the people, among the engineers, even for the people that you expect to have a solid knowledge of the die casting technology. Many people confuse TIXO, semi-solid, reo-casting, slurry. It's always the same. So we have a very rough idea of the processes, but without a right understanding of the difference between the different technologies. So what I want to say about the underappreciated advantages, that, and is my only message that I want to give you, GISS is not just a different way to fill a cavity. This is the point. So there are many, many other advantages. And I will return with pleasure to some of the topics that Mark has already underlined. Die life is one of the most important underappreciated advantages. Less tool wear, less manual deburring, less unplanned maintenance, fewer interruptions. Efficiency. So when you have less scrap, you have a saving in remelting, you have a cutting cycle waste, you limit the processing operations and the number of inspections. And also, you can shift to smaller die casting machine. Even this point has been already touched by Mark. And you can extend to application to sectors and to products that you cannot afford now with the standard liquid high pressure die casting, because it's too leaky for the thermal conductivity, too machining intensive, or made in other processes like gravity or low pressure. Why GISS is different? And why GISS cannot be put into the big list of the technology that are not applicable successfully in mass production? The reason is this one. The main reason is this one. Because GISS works above liquidus temperature. This is the main difference. All the other technology work in the range between liquidus and solidus. So what does it mean? It means what Yufeng repeat many times. This is dynamic, this is kinetic, it's not an equilibrium solution, it's not stable. So what is hot milk at the beginning becomes yogurt, becomes honey. I use the same image that Jess and Yufeng love to use. So this is different. It's different for all the other technology, and this is the reason can't be compared with the other technologies in the pros and in the cons. Can you make this start? Okay. The key point is the applicability, one of the main difference. GISS is very easy to install and to apply. So we have very few things to do. Add the stop to the loader path. The probe needs to be connected only to a standard, very standard nitrogen cylinder. So we have only power and nitrogen, nothing else. That's done. So installation takes half a day. Same mold, same alloy, same everything. We don't change the mold, we don't change the alloy. It's the same. Sorry, I'm back. So back to the issues highlighted by AI. Standard recasting is complex, GISS not. Standard recasting, tool change is requested. In GISS is not requested any tool design adjustment. Limited alloy, no. GISS can be used for not only for low silicon alloy, can be used for low silicon alloy, but not only. Is for expert only? No, there are very few parameters to control, very few parameters. Difficult part only? No, this is also very important. When you use GISS, you have to use GISS for all the parts. All the parts are suitable for using the technology. I move forward now to a study that we have been conducting for 2-3 years. I presented part of these study results even last year. And this study is about the evaluation of the range of advantages that we can be achieved through the GISS application. There are some benefits related to, of course, using GISS, but they are related to the die casting machine or to the die or to the die design. So change by casting machine or change when you change die. So if you have a scrape of impregnation, less shape, less machining, heat treatment, of course, all those things change and are related to the die and to the casting machine. If you have a bad mold, you have a lot of scrape. If you have a good mold, probably not. So it's very obvious. There are some cost savings. They are not related to the mold, but they are related to the part, for example, to the thicknesses of the part, and related to the die casting machine, cycle time reduction and die life extensions. And there are a third group of benefits that are always achievable, regardless the die performance, regardless the kind of alloy, regardless the die casting machine that you are using. Energy consumption, lube reduction, and the disposal cost reduction. So the study is the application of GISS at 3 Italian foundries for a couple of years time range with different conditions, different kind of holding formats. In one case, we have an electric basing furnace, one electric crucible, one gas fireball, different kind of loader, different kind of ladle. So we try to cover all the kind of possibility or the most common possibility in the foundry. The first thing is focus the attention onto the cycle time. Cycle time in all 3 foundries have been meaningfully changed and decreased. Sometimes more, sometimes less. But of course, the most important change in the reduction of the lubrication time and solidification time, mainly lubrication time, because of course the solidification temperature range decrease, so we don't need to spray a lot to 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 decrease the temperature. Another kind of saving is about the energy saving, cost of the saving. Of course, it would be the best would be to have the melting furnace at a lower temperature. But in the foundry, especially in Europe, you know, one single melting furnace works for many different die casting machines. So what we do is to reduce the single holding furnace of the die casting machine where the GISS is applied. But in any case, even the reduction of the holding furnace of 40, 50 degrees for the single holding furnace lead to a saving in the energy cost. Of course, in Europe, we are very sensitive to this point because the energy cost is very high. Now we are implementing a new technology in the Northern Africa, for example, and they are not so sensitive because the energy costs much less. But in any case, this is an important point that I will repeat even later about the sustainability and the carbon footprint. I mentioned that the GISS application reduced drastically the spray time. And okay, you can say, but okay, spray time and the sprayed liquid is not a huge cost. It's a very minimum cost because the dilution ratio is very, very low. So you have one part of lubricant for 100 part of water. So it's not so important. But it's not only the lubricant consumption, but all the process of lubrication, evaporator, waste disposal. So the waste sludge have to be disposal. So it's all the process is affected when you reduce the lubricant quantity. And these slides summarize the different savings per hour in the lubricant cost, waste disposal cost, and water recycle energy cost. Of course, there are other additional savings that we have not considered in this study. For example, the wastewater treatment maintenance, the waste sludge handling and storage. So there are many other steps of the process that is very difficult to consider in the study because are not so easily measurable. Okay, now probably this is the key slide of all my presentation, because what I would like to transfer you is this point that the GISS application lead not to isolated benefit one to each other, but the savings build on each other, so are very connected. So I told you this is not just a different way to filling a cavity. This is a new cost structure. This is a new shape of the foundry margin. Let's start from the first point. Okay, we know GISS reduces the thermal and mechanical stress on tooling. What is the outcome? Less tool wear and thermal fatigue. Then, less manual deburring, less unplanned maintenance, higher uptime, and fewer interruptions in the use of the machine. This reduces the internal scrap. Scrap reduction cuts remelt energy, and higher yield reduces the cycle waste. So fewer defects reduce post-processing and the number of inspection loops. GISS enables longer flow path, lower pressure, so also very important, we can downsize the die casting machine for a given part, or we can use the same die casting machine with different parameters. It means a lower operating cost, consume less energy, require smaller dies, and occupy less floor space. GISS work well with silicon and secondary recycled alloy. Lower silicon alloy are often cheaper and carry a lower carbon footprint. Can be a good financial lever in the carbon border adjustment mechanism that I'm sure you know, and other emissions-driven compliance costs. GISS gives access to parts that are out of reach for standard liquid production. Thermal management components, sand castings, long flow application. It means that the foundry can produce parts that are not selected on a discounted basis, on the price basis, but they are selected on performance. So weight reduction, thermal conductivity, tightness, and of course, you create a margin model that is more resilient, more robust, and you can face the market, not just waiting for the job to come with the standard way to get job from the quotation in the automotive sector, for example, but you can explore many other sectors, probably more with the higher margins and more profitability. Just to justify all my statements, I'm presenting now a cost model. You see on the right is a steering gear that we have compared the cost model with liquid and with GISS. The machine size at the beginning was 1,800 tons, but using GISS has been downsized to 1,350 tons. So thanks to the use of the technology, it has been possible to reduce the size of the machine. For the rest, you can see the standard applications difference. Of course, the main difference is in the standard liquid, you use the holding furnace as 770 degrees, and you can keep the furnace as 730. And you can reduce the die time for the solidification time less, and the spray time. So we have benefits in terms of temperature of the furnace and cycle time. Cycle times move from 88 seconds to 70 seconds. And at least the reject rate pass from 5% to 2%. We analyze the cost model. So like in the same way that Mark showed previously, we have now the production rate of the two kind of machines, the number of parts produced, the cost of the goods, the average daily downtime, and so on. The production cost saving is very, very important in 1 year, because mainly because it was possible to change a smaller machine. For the same reason, important savings in terms of tooling cost. Tooling cost. Here, the life of the die has been increased not double, just 1.5 times more. And the same for the plunger, and the same for the short sleeve. The machining cost, we have, of course, is due to the fact that we have less scrape. This becomes a saving in the machining cost of the final parts. Savings in the holding furnace, energy costs. Savings about lubricant and water treatment costs. And savings about the metal loss. Of course, we have a metal loss every time that we produce. So, summarizing, all those studies highlight that we can save 1.87 euros per part. So about 400,000 euros per year in relation to the productions and to the volumes requested. And if we want to analyze the return on investment, is very fast. But this was not the only point that I want to show you and to say. The most important point, in my opinion, is not this one. The most important point is to see what happens. Okay, let's imagine that we don't downsize the machine. What happens? On the left, you have the case if you change the machine. On the right, you have the case if you don't change the machine. And you see that only 0.2 euros per shot, so 11% of the savings are in relation to this choice. So even though you still use the same machine, you have a significant saving. And also importantly, let's imagine what happens if we have not any change in the reject rate. So the scrap rate remains the same. And this happens because sometimes we apply GISS technology to a good mold, to a good part, and the quality more or less remain the same. It's not always true that the quality of the part change drastically, can remain the same. But even when the quality, the final quality of the part, only 12% of the savings are related to the scrap rate reduction. So what I want to highlight, that there are many different kind of savings. All those savings are connected to each other. So you have not to imagine that the technology works only when the quality is definitely better or much better, or we have a wow effect, okay, we have applied, and now the technology change from night to day the problems. No, we have very massive savings, even when liquid and GISS are comparable in terms of quality. Even when we use the same die casting machine, so we don't downsize. Only 11% or 12% of the savings are related to this. There are many other factors that you have to keep very well in mind because they are really important. Finally, a very fast insight to sustainability. This is the same study that we presented at the Congress of the Solid State. So we compared liquid and GISS parts in terms of sustainability using, maybe some of you is familiar with the LCI, life cycle inventory. So you divide the processes in die preparation, metal preparation, casting, part finishing, and you analyze how much energy and how much consumption of CO2 are related to the single process, and which of those processes are changing the technology. So, for example, consumption decrease related to softened water, release agent, jet cooling, robot. So there are something that is changing and something not. In terms of carbon footprint, is calculated the equivalent CO2 emissions expressing contribution of each single foundry sub-process. So the foundry process subdivided in processes not affected by GISS application, and the not affected are ingot production, melting, degassing, and other processing affected by GISS application, holding, injection, trimming, shipment, and so on. So the GISS contribution is estimated as around 11% of CO2 emission reduction. So the GISS CO2 per shot is less 11% in terms of carbon footprint. This is very important now because many foundries are requested to produce documentation, to produce compliance with the emission-driven regulations. So being able to justify that your process is sustainable gives access to new job, new customers, new possibilities to have work from the market. So, summary. The die casting industry is changing faster. Costs are rising, market volumes are unpredictable. Traditional reliance on automotive is no longer enough to secure a stable business. The parts still demand higher ductility, tighter leakage requirements, better thermal performance than conventional high-pressure die casting can really provide. So GISS enables better quality, lower carbon footprint, and maintaining excellent castability. Results: smaller machine, less to wear, longer mod life, and lower production costs. So GISS is very easy to install. It's very easy to apply. And okay, I don't repeat myself because I have already mentioned all those points. Thank you.
Thank you, Tommaso. Any questions for Tommaso? I mean, one thing you can count on is good hard numbers from Tommaso every time. That was great. Any questions about any of his analysis that anyone wants to ask?
I have one question.
Yes.
Yes, actually, I'm reading this the slides. Actually, the cost saving is based on the machine rate around 300 euro per hour. Is that right?
Sorry?
I mean, the cost saving calculation is based on the
machine
rate.
You mean the cost of the...
Yes.
Yes.
300 euro per hour?
Per hour, yes.
Oh, that's normal in Europe, in Italy, or that's...
Yes, for this kind of size, yes.
Okay, got it. Yeah. Thank you.
That was a single example of a single machine.
Yeah, of course,
Yeah.
Can change from country to country. Is related mostly to energy costs, other costs. We have a lot of costs, like I mentioned, about compliance with emissions-driven regulations, measurability of the energy consumption. So European foundries are struggling a lot with the point of energy. So this maybe in other countries we know is different.
Great. Any other questions? Great. In that case, let's thank Tommaso one more time. Thank you, Tommaso.
Hold on, I'd like to give you a present.
Please. Can you put up the first slide? Don't worry. Thank you, Tommaso. Actually, there's an interesting, this is a great slide to lead into the next presentation because Tommaso says we can't rely on the traditional automotive industry, which has been such a big user of die casting in the past. And one thing that I've seen over the years that we've been running the GISS Forum is, you know, in the very first year or two, it was just talking about the technology, try to explain how the machine works, that kind of stuff. But we've moved a long way since then, as you can see from the presentation from Tommaso. And the next presentation takes that step further because now we're moving into the new industries. So I'd like to introduce John Ford, who's going to bring some perspectives of what we think is a exciting new industry for GISS. John?
Thank you very much. It's a pleasure to be here for the my first time at the GISS. I became aware of the technology, I guess maybe 5 or 6 years ago, and have followed the evolution quite a bit over the last few years. So it's great to meet Jess finally and present on maybe certainly a very different industry, I think, to a lot of what you guys are used to kind of seeing and understanding. So I'm looking at very specifically aerospace aluminium shape casting opportunities. So something typically not associated with high pressure die casting over the years. Very quick, a little bit of background on me. I studied at the University of Birmingham, where I think anyone who's aware of casting technologies, where Professor John Campbell was based. I came in at the end of John's role leading the casting department there, but I've taken a lot from his concepts and theories around metal turbulence and reducing metal turbulence and improving metal quality. Part of my doctorate was working on cast alloys for the aerospace industry, so looking at particularly the aluminium copper-based system, so A201, A206 type alloys, quite complex, quite challenging to utilize. Ended up developing a new alloy, the A200X, or A205 as it is now designated, with a company called AirMed International, where I went on to spend the next 9 years as the lead technologist, productionizing that alloy from kind of proof of concept up to full commercial readiness and licensing it to other aerospace foundries. So quite an unusual situation. I got to travel to the vast majority of the top aerospace foundries in the world, something that is normally quite an insular society, where it's very difficult to get into other people's foundries. So I got to understand a lot about what was happening in other foundries. And everybody believes they're doing something different and doing something brilliant, but in reality everybody is doing the same thing and making the same mistakes and kind of holding each other back ultimately in progressing. As part of that role, I had a kind of a very broad kind of remit, so I was looking at alloy development in terms of metallurgy and the fundamentals in the foundry, but really looking at NPI optimization, knowledge transfer, so trying to transfer complex knowledge to engineers and at end user level to the foundries, but also, I guess, probably interesting, interaction with industry governing bodies to try and get the alloy into the MMPDS handbook, which is the Bible for aerospace design engineers ultimately, and it's working with AMS to devise specifications. So a good understanding of the challenges that are required to get something new into and accepted in the aerospace industry. I won't go into all of this, but ultimately I work with foundries, so I work specifically with foundries who are looking to do things differently. I have got an interest in additive manufacturing, largely from how it can complement casting, so looking at hybrid cast additive manufacturing routes. The A2OX alloy was atomized and is now a very successful powder-based material for additive manufacturing. Got a significant interest in some of the slightly different additive aspects, so direct energy deposition, so wire arc additive manufacturing, so building or 3D printing onto existing cast structures and things like that. So more hybrid cast additive than straight additive. And then I work with the industry, with the end users, looking at, I guess, trying to educate them in terms of what's possible with casting, why casting is perceived the way it is currently, which is pretty poor, which I'll go into, trying to transfer knowledge, and trying to work with foundry supply chain management to help foundries communicate better with their customers. So that's a little bit of background. To understand where aerospace casting is, it's important to kind of look at the development of it over the years. And we can go back to, really back to the 1960s. So here we've got, this is the kind of scale of, the size of this circle is, I guess, representative of the scale of research that's going on in casting and shape casting. I'll call it shape casting as opposed to casting, because you've got big DC casting for ingots, but shape casting of components. In the 1960s, there was a huge amount of work. Casting was one of the only ways really to make complex shapes. High-speed 5-axis machining wasn't developed yet. So casting was a key foundation manufacturing technology of the aerospace industry. If you look at things that were developed around this time, you have the 300 series, so 356 alloy was developed in the 1960s, 357, C355. All of these alloys have their origins around the late 1960s. Also the 200 series. So effectively all of the materials that are used today have been around since the 1960s with very little change in the specifications. So that gives, I guess, the first indication of maybe a lack of progression is that we're still using alloys that were developed over 60 years ago. There were some very interesting things going on at that time. You've got nucleation theory in terms of grain refinement and the understanding of how to utilize grain refiners, and the development of things like age hardening, so an understanding of how to age harden alloys, and that's really where these alloys got developed. At this point, the OEMs typically had their own foundries. So Boeing had a huge foundry and loads of metallurgists and loads of casting engineers. Lockheed Martin, these alloys were, the 200 series in particular was developed by Lockheed Martin. So it wasn't developed by a foundry, it was developed by an aerospace company in their internal foundry. As we move into the 1980s, the OEMs decided they didn't want responsibility and ownership of the castings anymore in the casting process. So they wanted to shift to a supply chain, or a wider supply chain of castings. So you see in the 1980s, in-house foundry decommissioning, so the OEMs shut down their foundries, and there was a proliferation of smaller foundries all around the world. So we went to North America, saw a huge proliferation in aerospace foundries, Europe and France particularly, and the UK as well. What we see here is fundamental development of alloys. As we move into the 1980s, we see a step away from developing alloys is very expensive. It's OEM level spending because of the requirements around qualification in the aerospace industry. As we move into the 80s, rather than look to develop new alloys, which is very expensive, the foundries looked for process improvements. How can we make the casting process better, more repeatable, more reliable? So you start to see things like counter-gravity casting becoming more utilized. Process simulation became, the starting kind of seeds of process simulation began. Things like rotary degassing started to develop and be optimized in terms of how you treat metal and the understanding of how to make metal better. You can see here there was a revision to the 357 spec. I say revision, it effectively tightened the specification to help achieve higher properties. Very little else has happened from the 1960s to kind of mid-1990s. The year 2000 and around that time was a real critical time for the aerospace foundry industry. There was a huge development in machine from solid capability. So the development of 5-axis high-speed machining suddenly meant that you could machine components of a similar complexity to, not the same, there's clearly an advantage in terms of complexity with shape casting, but you could start to make more complex shapes. And the general view of casting at this point in time is that it was significantly less reliable, repeatable and consistent than machining something from solid, from a billet that you got in the door. You could buy the billet from numerous sources, you did your machining, the billet was NDT tested prior to arriving, you machined it, you did your die penetrant afterwards. The scrap rates were much lower. It also meant that you could use higher strength alloys, the 7000 series particularly, 2000 series initially, but then moving into 7050 and 7075 in more recent years. So strength increased, strength capability increased, you moved away from the scrap rates of castings, and what happened at this point is really critical in terms of, this should say 2020, apologies, so we're into 2020 here, not 2000. What we saw was a response from the foundry industry to the machine from solid capability was not to invest further to develop the technology, but was to look at how they could take cost out of their process. How could they make the castings cheaper? So what we saw was, rather than an extension of R&D, the R&D dramatically shrunk in terms of complex technical R&D into new alloys or new processes. What we saw was, it was quite a sensible move. They looked at how they could squeeze cost out of the process. So they got better and better at making castings of the same quality, which was relatively, it was average, it was highly variable, but they got better at making it cheaper. There was no real, there has never been really a coordinated research development technology structure for castings. As I said, casting is quite an insular, it may be different in the automotive industry, but it's a very insular industry in terms of aerospace. Everybody likes to keep their knowledge internal and they like to develop it themselves, and that's challenging from a supply chain perspective from the aerospace end user. They don't want bespoke processes and they don't want niche alloys. They want something that is, historically they didn't mind that, but certainly in recent years they want more recyclable alloys, less variation in alloys. The aerospace industry have a lot to answer for in this. It's incredibly conservative and it's incredibly difficult to make changes in the aerospace industry. It takes a long time to get things accepted. That is changing, and they've accepted that has to change because the requirements for weight saving and carbon footprint reductions means that they can't take 20 years to approve a new alloy and to develop it. They have to be more reactive. So this conservative ethos and the lack of process competence meant the foundries were very reluctant to do the work because they could spend a lot of money developing a new alloy that would never see. So Aeromet and the company I work for developed the A205 alloy, so really went out on a limb to try and develop something, and it was a fairly painful experience in terms of the development, but it is now, there are aerospace castings flying on airplanes that are A205, so this was the last real alloy development in the aerospace industry in terms of a new alloy. But even this is a variant of A201, so even that isn't a new kind of alloy. Some of the other issues is, as casting became less interesting to the aerospace industry, the desire to go back and look at the specs and say, okay, the spec was developed in 1967, maybe we should have a look at developing that, and is there a way? So this D357 specification, it is definitely more refined than the 357 specification, but it doesn't tell you how to meet those higher properties. You could follow everything within the specification. So here we have the kind of step change in properties. We've got A357 here, which is 220 megapascals proof, 280 and 3%. The D357 alloy is 275, 345, and 3 to 5%. So it's quite a big step up in properties. But there's nothing within the specification really that tells you how to achieve. So you could follow everything in the specification and still not meet the properties, which is where the lack of confidence came in the aerospace industry. So they would go to foundries and say, can we have something in D357? And the foundry would make the part, and they would be nowhere near these properties, or consistently near the property. So it suddenly became, well, that would be lovely to have, but I can't get it in I can get it in one foundry in the US or two foundries in the US. This process, so one of the developments in the technology is controlled solidification investment casting. So investment casting, but trying to drive the solidification rate. And that was one of the key steps in the D357 process. So higher cooling rates, lower secondary dented arm spacing, smaller intermetallics, better properties. So that's one of the key requirements. That is quite a niche. There's five foundries in the world have that technology. There's other technologies have evolved in recent years. So most, I would say there's maybe 10 aerospace foundries in the world that have controlled solidification investment capability, which isn't a huge number. In the background, we've still got the A201 and A205 alloys, so they're significantly higher strength. So 435, 485, 3 to 5%. The A201 alloy is almost universally regarded as uncastable for complex shapes in aerospace. A205 is better, but equally it's constrained to licensees of the technology, so it's still this constrained supply chain, which isn't that attractive to the aerospace industry as it moves forward. One of the other issues is from 2000 onwards, when it came to designing a new component, casting was never considered as is there any other way to make it except casting? And then they would design it as a composite fabrication, or as a machine from solid component, or as a fabrication extrusion machine from solid. So what would happen, the component would be designed, the design would be sealed. They would come to a foundry and say, well, okay, could you quote on this, or do you think you could make this part? At which point, all of the benefits of going to casting have been designed out of the component. It's designed as a machine from solid component. So you say, well, we could, but we could take a lot of weight out of the component, but the design has changed, so there's no interest in so either make the shape, which is not really taking advantage of the casting process. So that's really where we've kind of got to in recent years. This is something that an engineer said to me when discussing castings and why we could use better castings, and he kind of said the main problem with castings is that they have to be cast. So they like everything else about it. They love the design freedom, they love the flexibility, they love all of those things, but fundamentally they said, as soon as we get into making it, the repeatability and the consistency, it just isn't there to give us. There's still lots of castings utilized, but to really push forward, and I guess the area I'm most interested in is moving castings into the structural, or the aerostructures side of things. So at the minute, castings are systems based, and they're small, and they're pumps and fuel metering unit, housings, electronic boxes. But getting into the big structural stuff, as you'll see later, that's where the market really starts to increase, and it's where it should be utilized more because of the potential for weight saving ultimately. So a little bit of metallurgy. One of the key challenges, there's lots of challenges with casting, but one of the key challenges really is melt cleanliness, so the quality of the metal. And I think maybe the one difference in the aerospace industry is the quality requirements are extraordinarily challenging. So every part is 100% radiography checked for the high strength, high stress kind of applications. Every part is 100% dye penetrant tested, and the spec is ASTM 2175 grade B. So you're getting close to zero defect on X-ray, which is challenging. One of the main issues is oxides. Everybody has to deal with oxides. Every industry has to deal with oxides. As I said before, I came out of Birmingham University, so Professor John Campbell has a very strong view on turbulence and turbulence in metals, which I agree with. And this is around the formation of bifilms or double oxide films. So it's turbulence-related events where the oxide film falls back on itself, so it doesn't fuse back into the metal. So you've effectively got a series of cracks within the liquid. So the liquid metal is effectively cracked, pre-cracked before you've even made your component. So these they also provide nucleation points, and this has been proven kind of recently for hydrogen porosity, shrinkage porosity, intermetallic formation, eutectic formation. So they're a strong nucleant of everything. Problematically, hydrogen porosity. So one of the guess one of the most interesting aspects of working with Professor Campbell has been the concept that hydrogen isn't the problem. It's the presence of biofilms in the metal means that the hydrogen has something to nucleate on to come out of solution. So it's the biofilms are more the problem. The hydrogen isn't necessarily the problem. The other challenge with aluminium biofilms and oxides is they're typically neutrally buoyant, and they have an air gap in the middle, which means that they float within the melt, which makes them incredibly difficult to remove. So they tend not to sink or float. And I guess one of the key things to look at here is there's a number of areas where these defects can be introduced. Some we have control over as a foundry, some we don't. So you've got the primary ingot manufacturer, so you buy your ingot in. Doesn't matter what you do in the foundry, ultimately, if the metal you're buying in is full of oxide and defects, then there's only so good your metal is going to get. So this is challenging to resolve at a foundry level, but it is possible to resolve at a raw material supplier level, and it's trying to work back up the chain. Foundry loading, when you load up a furnace, you're loading up an ingot that has effectively got a very big oxide skin on it, which melts and gets incorporated into the melt. We use things like rotary degassing, so metal treatment, to effectively kind of homogenize the melt. So we've got lots of oxides in there. Rotary degassing removes the hydrogen. It also shears and breaks up bigger oxides into smaller oxides, so they become less detrimental. But they still have a significant control over the potential properties achievable from that alloy. And then mold filling, which is, most aerospace foundries have a good handle on these first three. So they buy from good suppliers. They know that they're aware of the impact of quality of incoming ingot. They load their furnaces as best they can. They try not to pouring from furnace to furnace. They try and use filter socks and things to control turbulence in terms of bulk metal transfer. In terms of metal treatment, they all run pretty sensible rotary degassing. They've baffles, they've used using flux and trying to control oxide. So there's a high level of awareness around these kind of areas, even metal transfer. So you see more and more foundries move into counter-gravity, so they're looking to push the metal uphill rather than gravity pour, which induces turbulence. And I guess but there is still, I would say, I don't know, maybe 2% of the aerospace foundries are using counter-gravity, and these are the high-end top aerospace foundries use counter-gravity in all of their manufacture. This is interesting. So this work came out of John Campbell's time at Birmingham University. It's quite a useful kind of videos just to document. I think the vast majority of aerospace foundries have choke-controlled gravity port systems. So the metal comes down, is choked at the bottom of the sprue, fills a runner bar, and comes up into the casting. So this is even in a bottom gated, so kind of seen as good practice from a turbulence perspective. But there's very little consideration given to the metal flow in the sprue or in the runner bar. And you can see all of this, so all of this here is potential entrained air, and with entrained air you get entrained oxide. So you can see the filling of, so this is a real-time X-ray of a mold filling. So it's a mold in an X-ray machine being filled. So this is a real-time representation of the turbulence within the mold. If you develop running systems, and this is based again around Professor Campbell's kind of theory around naturally pressurizing something, so you develop a naturally pressurized system that exists in other liquid flow processes but have just never really been applied to casting. You can design the running system to constrain the metal. So you try and constrain the metal. You can see you're filling in a much more quiescent or much more calm, controlled way. So you're not introducing all these first three. They still may play a role, but the mold filling side of things, you can manage gravity pouring in a much better way. Counter-gravity effectively eliminates, gives you the same kind of result, but counter-gravity equipment is expensive and big infrastructure changes. So there are small changes that you can make, and this is applicable in the. So I've worked since I've become kind of an independent person. I've worked a lot with the automotive industry as well. People looking at, I guess, trying to cast maybe slightly higher end motorsports, but looking to make kind of electric motor housings where they're looking for what they don't realize. They're effectively asking for aerospace grade castings, but they want them at high pressure die casting prices. So they want to pay whatever, $20, $30, $5 a casting, but they want it to be leak and pressure tight. they want to be able to machine the whole thing, and so you're getting into an understanding of what's required to do that, and it is possible with gravity casting without major changes to molds and tooling and things like that. So I think this is an interesting, this is one of the challenges, and this is probably one of the single biggest reasons why aerospace castings have been viewed as inconsistent and unrepeatable and very poor in terms of repeatability, is that the filling of the mold has not been particularly good. And very quickly, this is some work that John has done over the years, looking at, I guess, the evidence of biofilms. Here you can see they can be incredibly thin, nanometers thick, very difficult to detect. We can see here, this is some work where they're looking at a quality index for alloys. How can you do? There's been lots of quality indexes or indices over the years in terms of how to characterize quality of a casting. This is probably, I think, probably the simplest, which is looking at the yield stress versus the ductility. And when you start to plot this, you can see there's a line very clearly where, with increasing yield strength, there's a point above which you can't achieve higher ductility. And the view is ductility is driven by defects and the presence of defects. You can see the scatter this is from a number of different studies, so the scatter is huge. So you're down here. So if you look at this in terms of what the material quality means, you've got high damage, moderate, low, very low, and there's currently nothing really above this level here. So this is the target, ultimately. So I guess what's interesting is this quite clear boundary where it's difficult to get ahead of, but also it's the scatter in data is significant, and again that all plays into the repeatability or the lack of it and the concerns around that. For context, where do aerospace specifications currently sit? Down there, which suggests that most foundries are operating in the very high damage kind of area. So the specifications kind of determine where you need to aim your process. If you don't need to exceed the spec, so what's the value in trying to push higher and higher, because the spec is the spec, and that's one of the key limitations, is trying to push the desire to make better castings to the forefront. That needs the aerospace industry to get involved as well. Yeah, so there's your A357 spec requirements, D357 slightly higher. There is evidence of applying good practice, good metal treatment, naturally pressurized running systems that show properties consistently in this region here. So it is achievable. You can get 20% plus, so between 20 and 25% consistently in A356 with just the application of good metal treatment, good metal handling. So I've kind of mentioned the perception of the aerospace industry of castings quite a bit. Is pretty low. If you look at it as a come from solid and a number of different parameters, if you look at the size envelope, it's not too different. Machined from solid. This is purely machined from solid, so not looking at fabrications and assemblies. So it's a machined component you're into. Size envelope isn't hugely different. Design freedom is definitely better in casting, so we're ahead here. Component quality, it is dramatically, the view is it is dramatically lower. Process robustness, again, dramatically lower. And this data is generated from discussions with end users, OEMs, tier ones. This is their view. Mechanical performance, that's fundamentally limited by the alloys. And interestingly, the inability to shape cast things like 7000 series, which is where the GISS technology suddenly starts to become increasingly interesting. So the mechanical performance is lower, but only because the limitations in terms of casting alloys. Process sustainability is significantly higher in casting, and this is the key reason for a resurgence in interest in castings, is that there's a desire to cut, move towards sustainability, so lightweighting, looking at burning less fuel effectively. How can you burn less fuel in an aircraft? Taking weight out is critical. If you can increase your design freedom, you can make more complex shapes, you can use generative design and topological optimization to make more efficient components, then these can only really be made with or additive manufacturing, but additive has kind of similar constraints and limitations with casting ultimately, and it's much more expensive. The other key challenge is the perception around, well, it's not a perception, it is rate capability. So the rate capability of conventional aerospace casting processes is low. It's high, it tends to be high complexity, low volume. And that's just the nature of there's no desire really for higher rate capability. Looking to get into aerostructure components, rate capability is a consideration. It's the cost. In the vast majority, we'll see in a second, the vast majority of aerospace components, the margin is very high. You're talking at $100,000 per casting in some situations where you're making that for about 50% profits on a casting. It isn't unheard of. So it's a very different industry to the. But if you're into scrap issues, if you're scrapping a $100,000 casting that's taken 2 weeks to fettle and X-ray and the amount of cost that's gone into it, then it's very quick. The potential for profits is there, but it very, very quickly gets hit when you start to run into consistency issues. Looking at I guess what are the technologies that are out there? I think you're probably all aware of a lot of this. We've got die casting, which you guys know an awful lot more about than me. So you've got vacuum assisted high pressure die casting, squeeze, LPDC, gravity and tilt, semi-solid type processes. Sand casting, gravity, counter-gravity, vacuum process, lost foam. Ablation casting is a more recent development. And investment casting, you've got kind of lost wax, gravity and solidification controlled, plaster mold stuff, counter-gravity lost wax, lost foam again. So lots of potential. There's lots of ways of making aerospace castings, but in reality, the vast majority are gravity sand cast and gravity lost wax. Increasingly solidification controlled lost wax, but die casting is a very, very small proportion of the castings produced, and they're almost entirely non-structural or non-engineering, so cosmetic kind of handles on overhead compartments and cosmetic kind of things. So the reason really is that the volume requirements have never been there, I think, to look at die casting as a potential solution. So with the rates not there, there's no desire from the die casters to look at making better quality castings. So it just hasn't evolved really. But you'll see a little bit later that is changing. Typical aerospace components relative to the casting process, and approximate scale here is about this. This is a 1.5 meters. So we've got big gearboxes. These are typically sand cast. Things like control columns. This is you're moving into, could be sand cast, could be investment cast. Lots of pumps, high pressure fuel pumps, low pressure fuel pumps, fuel metering units, actuator bodies, these kind of things. This is a structural component, so it's a winglet for the Embraer Phenom. This was made by my previous company, Aeromet. This is an interesting product. It went from a 60-piece assembly to a one-piece casting, a two-piece casting. So it's joined in the middle. But that's a big investment casting, 2 mil wall thickness, so challenging kind of components, but low volume. Into kind of complex electronic boxes, again, which I think a lot of people in the room are probably very familiar with and can see maybe a potential application if the numbers increase. And things like gimbals and brackets, and a lot of these are kind of defense-based kind of products. But that's a typical kind of, it's low volume, high mix, high complexity, so it suits sand and investment. So coming out of the foundry industry, it was really, I started to think about what's kind of required to, the potential for castings is huge, potential for aerospace castings is huge, but it hasn't really materialized or evolved much in the last 50, 60 years, well, call it 20 years. And really it's the entire value chain needs to change, which is quite a big step. But it is happening, and it's happening quite slowly. So we're into things like industry perception needs to change. That's kind of people like myself need to work with that. It happens through academic engagement, so working with universities and academia. Materials need to be looked at. Design and process modeling need to improve. Mold manufacture, so looking at automation, digitalization, those kind of things, 3D printing. The casting processes themselves, post-processing, there's loads of scope to advance and develop. Effectively, there's potential to evolve and advance every single area of area. We're not looking at one single area like a material needs to change. There's potential to change everything. And that's really where, and I guess that's not to say that there isn't things happening. There's definitely things happening in the aerospace foundry industry. There's lots of work going on co-design, so design for manufacture, looking at advanced metallurgy, but it's very difficult to apply for the reasons I said before. It's acceptance and material quality and characterization. There's work going on metal casting technology. There's lots of stuff on indirect additives, so 3D printed sand. There is work going on automation and digitalization, but it is decades behind the automotive industry in that area. What's really missing is kind of bringing it all together. So this is kind of the evolutionary stage, and that's happening, but really this kind of revolutionary stage of bringing it all together into designing for a process that is better and taking advantage of a better process in the design stage, and having engineers, when they go to design a new component, think, I might design it as, or it could be designed as a casting, so let me think of casting before I go and design it as a fabrication or as a machine from solid component. There's lots of potential benefits to evolving, which is improve sustainability, enhance performance, enhance quality, enhance productivity. So there's a lot of easy wins in here, I think. So looking at where we could be, where we are, is what we discussed already. This in reality is where we actually are. If you apply all of the knowledge and everything that's available out there to make better castings, then you can start to achieve kind of definitely better process for component quality. And they're the key areas, really. These two are what holds back casting development. And it's quite easy to make improvements there. Where we need to be is really competing more directly with machine from solid. One of the biggest challenges there is rate capability and size envelope. And I think that's where the GISS technology starts again to become, and in terms of mechanical performance. So if we could cast 7000 series at a high rate with good quality, then the aerostructures market opens up, which is a pretty significant market. In recent years, I've been involved with the ATI, who are the Aerospace Technology Institute, who are a government-funded body in the UK, and they develop the UK's technology strategy for all aerospace. And they routinely issue their strategies. The most recent strategy is Destination Zero, so looking at sustainability. One of the things I guess made them aware of was the potential of casting, and it's not something that was high on their agenda because they're driven by the OEMs and the tier ones who don't really have any interest in casting. So making them aware of the potential, particularly around sustainability and lightweighting, we started to work on an aerospace aluminium shape casting roadmap. So what is actually required to make casting much more applicable and usable? And it's a bit of a busy slide with lots going on, but you can see there's some prerequisites, which is design capability. Factor one design, if you wanted to use investment casting or shape casting to make a critical structural application, so an aerostructure that is a critical structure, then you have to, there's an assumption that casting is inherently variable. So alongside your design factor that you will put in to ensure safety, there's an additional factor, a casting factor, just that you have to put on top of that again, because the assumption is casting is variable, and so it's typically 1.6 or greater. So you suddenly you could design the component for a casting, you then put your design factor on and then your safety factor on, and suddenly all of the benefits of designing that or optimizing the design are gone because it's 30–40% heavier than it needs to be, and they go, well, it's actually heavier than the machine from solid component now, so what's the benefit? So this is all around process control, and it's process automation, digitalization, data capture, that's critical. Some of the areas that need to change are high-performance circular alloys, so maybe new alloys, or looking at existing alloys, but making them using, I think Thomas mentioned secondary metal. Secondary metal has a 95% lower carbon footprint than primary, which is enormous. So if you can move to secondary metal to make high property or high performance components, that's a 95% saving in the material carbon footprint just in that alone. So huge potential there. Digital mold manufacture, so robotic assembly, 3D printing, hybrid molds, enhanced liquid metal engineering. I think GISS probably fits into that a little bit as well, if we talk about liquid metal engineering. So just doing things with the metal that is slightly different or slightly unusual to what would normally happen. You can see it's in here already, but ultra high repeatability metal transfer. How do you get the metal into the mold repeatably and consistently and in a low turbulent way? And that's these are the different ways of doing it. This is where the GISS technology kind of definitely sits. So these two, but I think the expertise in the room today, I think, has a huge amount of experience in all of the ancillary things, because the automotive foundry and casting industry is just so far ahead in terms of automated processes, data capture, digitalization, all of that. And there's a real kind of high level awareness of that. If we look at the roadmap out to kind of 2030, 2035 plus, we've got some of the key areas. So we've got approvals, allowables, and specifications. So there's an understanding from the aerospace industry that they have been difficult over the years, and they've been reluctant to change and slow to accept new alloys. So these things need to change. They need to go back and look at the specs. There's this area here is critical, and I think probably something critical for any new technology, particularly GISS, is this digital qualification. So as it stands, if you bring a new alloy to an OEM or a tier one, they'll say, well, I have to spend, I don't know, £1 million to generate the data that I've got for A357. I've got 50 years of data for 357. It's not very good, but I know how it's going to behave, and I'm confident in my understanding of it. How am I going to get that with your cast 7075? Now, the fact that it is an existing alloy is beneficial. It's not something new. It's an existing alloy. But there is definitely emerging technology around digital qualification, so using machine learning and developing software platforms where you can adjust chemistry and heat treatment and get accurate data out for lots of parameters. That is key in terms of moving forward, and there's an appreciation of that from the aerospace industry. Design, so actually just designing for casting, fairly simple. Manufacturing and processes, you'll see here there's a key requirement, a cross-sectoral knowledge transfer. So it's looking to other industries, like the foundry, electronics, automotive. How do you do what you do, and can that be pulled back into the aerospace, or evolving aerospace manufacturing technology? And then materials. So optimizing existing alloys, things that have been around for quite a long time, developing new alloys. And I think the GISS process sits kind of very strongly. It is effectively kind of like a new material in terms of how it behaves. So it's very interesting. Covers, if you think of the technology, it covers quite a lot of these points that have been developed with the aerospace industry kind of independently. In terms of alloys and material evolution, so 2020, 2025, out to 2030, you're looking at same alloys, but just do it better. Look at refining things. Castable 2000 and 7000 series, that is currently not achievable at all in conventional sand or investment processes. The freezing ranges are too complex, the composition is too difficult to work with. So it's highlighted as a key requirement. There is no way of doing it, with the exception of, I think, semi-solid and particularly the GISS technology. So this is a huge opportunity here, I think. And then as we move into digital alloy development and approval, so new alloys, different architecture, aluminium cerium, things like that are showing some promise. And then new high temperature, high strength, so metal matrix composites, lots of different aluminium scandium. It's been around for a long time. It's been there's lots of it's been the new material for about 40 years. It's never quite got there. Yeah, so there's clearly a a role here for the ability to produce complex or near net shapes in 7000 series and 2000 series alloys. Some of the types of structures. So when we get into the aerostructure, so these are components that are not possible, currently not cast, and would never be considered really as a casting. But casting lends itself very much to making those components. If you could make them as repeatably and as consistently as you could machine them, then you could change the design dramatically and optimize the design and save weight. And I think there's potential across all of those. So we're into kind of big central ribs, leading edge ribs, emergency access doors, potentially full doors. I think you've mentioned, spoke to someone about doors, but that's been floating about for 30 or 40 years. Can we cast a door? And Boeing tried and have done it, but the view on doing that 10 times the same way was it's not going to happen. So it's all about repeatability and consistency. I guess maybe just to look at what is the kind of market, what are we talking about here in terms of what is it of interest to people in the room maybe? And this again comes from some work by the ATI. It's in their strategies, their composite strategy and their future strategy and their near net shape strategy. So you're looking at, if we look at aerostructures, which is the key interesting area. Well, if we look at the existing global aerospace kind of aluminium market it's small, talking about 700 million. It's not a particularly big market. It's predicted to grow to maybe 1.1, 1.2 billion by 2028. So it's still big, but it's not huge. But if we start to factor in aerostructures, by 2030, 2035, you're into 40 billion that's the value of aerostructure components. That's just aerostructure. So you look at engine. Engine is kind of fits in with the existing components. Things like landing gear. Again, that's another 10 billion. Landing gear is a key kind of area to look at for casting actuators and things like that. So you're into like a 50 billion, potential 50 billion pound, so $75 billion market. Realistically, you're not going to get all of that market if you can cast things. But this is some work again done by the ATI looking at what's the potential for near net shape transition from machine from solid, and we're still in the kind of 11 billion kind of. They've identified 11 billion pounds worth of product that could realistically switch to near net shape, whether it's 3D printed or forged or things like that. So it's a big potential market. In terms of barriers to entry, there's lots. Just getting into aerospace, people again to listen to you about new technologies is challenging, but really the fundamental that has stopped the vast majority of people getting into aerospace is quality and repeatability. If you can't do that, there's no. And when we talk about quality, it is. You can. Some people may be aware of the ASTM radiography requirements, but this is effectively zero defect on X-ray. So you're into pinhole, 1 or 2 pinholes per inch cubed. So it is challenging. The dye penetrant, this has been a huge problem for a lot of foundries trying to get into aerospace from automotive, particularly sand foundries, because you're effectively it's still pretty much zero defect on dye pen. There's no impregnation. There's no capability or allowance for impregnation, so the casting has to be good. They do use HIP, but HIP should be used to enhance, not to save a casting. It should be used to enhance a casting. So if we can get the quality or repeatability, then the properties is the key. And I think if we look at the split between the two, for the GISS technology, if you could use GISS technology to increase repeatability and consistency, that's a huge potential. You're not going to get maybe better properties. Maybe you will get better properties, but you don't need to have better properties in 357 and 8201. If you could make it more repeatable and automated, that alone is enough to get a lot of interest. But if you can do that with 7000 series, then there's a huge amount of interest. So I think that is it. Any questions?
Thanks, John. That's a very different set of perspectives than we're used to
Yes,
hearing.
yeah, I think
That
it's
was
probably
great.
quite different.
Any questions? Different industry for a lot of us. Any questions or thoughts? One thing that I was amazed by was very small quantities and very long cycle times. So very different industry than
hugely
automotive.
different. But with the aerostructures, we're talking, most of those parts are, I don't know, at the highest rate, you're looking at maybe 2,000 or 3,000 a year. The aerostructures bit are maybe 3,000 or 4,000 a month.
Oh.
So you're starting to get into higher volume.
I know Mark is a giggle casting expert wherever he is, so maybe we could, right? So you've touched some of that a little bit in the past. Excellent. John, thank you very much. Okay, we have one last step. This is a tradition of ours. Please. Thanks for thanking our guests. Thank you, John. Right. All right. One last thing before lunch. Every year at the GISS Forum, we give an award. In fact, there are award winners sitting in the room right now from past GISS Forums. Today, Jess would like to give an award for sustainability. So for the best application that we've seen in the last year from Dyson Company Limited, please join us up front. Thank you. So this is a living example of the energy savings and the CO2 emission reduction that we heard about earlier. Thank you very much. Right. Okay. Next agenda item. Best partner. Nantong Genshin Mold Company Limited.
You want to join?
One more best partner. Wuxing Beer Machinery.
Okay, we also have 2 more advisory board members, and I would like to, okay. First one, welcome Jason. Please come up. Golden dumbbell. And the next board member is Dr. John Ford. Made of gold. 1 kilo of gold. Thank you. And I have a surprise. We have GISCO executive promotion. The first one, Dr. Yu Feng, has done a great job restructuring GISCO. He's a strong leader of CEO of GISCO. He had a mission to make GISCO sustainable, and he has accomplished that, his mission. So I now promoted him Vice President of GISCO.
Oh, thank you.
So you have 2 kilos of gold.
Thank you. Thank you very much. Thank you so much. Thank you. Thank you. Thank you.
Okay, it was a surprise. He didn't know that before. Also, the next one, my former master student and PhD student and co-founder of GISCO and my love friend, Dr. Sangop Thanabarungkun, is now Vice President of GISCO. 2 kilos of rose gold. Okay. Thank you very much. Now it's time for lunch break. And we will come back at 1:30. And we will start the next session 1:30. And we may change a little bit for product review first, maybe 5 minutes, and then U-Forum will start. Okay. Thank you. Thank you very much. See you after lunch. We will take.
So in your presentation.
ขอบคุณมากครับ